Hey everyone, so when you first learn about infinite series in calculus, it usually boils down to one simple question, right? Does it converge? But it turns out there's a much deeper story. See, not all convergence is created equal. Some series are rock solid, while others, well, they're kind of holding on by a thread. Today, we're going to pull on that thread.
So, let me ask you this. Is all convergence created equal? I mean, if you have two different series and they both add up to a nice finite number, are they basically the same? You'd think so, but the answer is a big fat no. And understanding why, well, that's where you really start to see just how weird and wonderful infinity can be.
Think of it like this. On one side, you have sturdy convergence. This is like a solid brick wall. The terms are getting small so incredibly fast that even if you made them all positive, the series would still add up. It doesn't need any help. But on the other side, you've got fragile convergence. This is more like a delicate house of cards. It only works because of this perfect, delicate balancing act, where the positive and negative terms cancel each other out. You mess with that balance and the whole thing comes crashing down.
All right, so here's our game plan. We've just introduced this tale of two convergences. Next, we're going to give these ideas their proper mathematical names. Then, we'll walk through a step-by-step test to tell them apart. After that, we'll put the test to work with three classic examples. And finally, we'll get to the big question: why does any of this actually matter?
So we've set the stage. We have this idea of two completely different ways a series can converge. One is strong and unconditional, the other is fragile and totally dependent on cancellation. Now, let's make it official.
Okay, it's time to put some real math terms on our sturdy and fragile categories. These are the official names you're going to see in your textbook and, yep, on your exams. Absolute and conditional convergence.
First up, we've got absolute convergence. This is our sturdy guy, our brick wall. It's super simple. A series is absolutely convergent if you can literally ignore all the negative signs. Just take the absolute value of every term, and that new, all positive series still converges. It's strong because the numbers themselves are just shrinking to zero that fast.
And on the flip side, we have conditional convergence. This is our house of cards. Here's the deal. The original series, with its mix of positives and negatives, converges just fine. But the moment you take the absolute value of the terms, it all blows up and diverges. It converges only on the condition that you have that perfect cancellation happening.
So what's the big takeaway here? It's simple. Absolute is stronger. Way stronger. In fact, here's a pro tip. If you can prove that a series converges absolutely, you've automatically proven that the original series converges too. No extra work needed. It's a fantastic 2-for-1 deal.
Okay, definitions are cool, but how do we actually use this stuff? How do you look at some random series and figure out which kind it is? Well, lucky for us, there's a super straightforward diagnostic test we can follow every time.
Here is the foolproof plan. Step 1, you always check for absolute convergence first. Make all the terms positive and test that new series. If it converges, you stop. You're done. The diagnosis is absolutely convergent. But if that absolute series diverges, then, and only then, do you move on to step 2. You go back and check the original series. If the original converges, then your diagnosis is conditionally convergent.
All right, enough theory. You don't learn math by staring at definitions, you learn it by getting your hands dirty. So let's put our diagnostic test into practice with 3 different case studies.
First up, we've got this guy, the sum of -1 to the n over n cubed. Now, it's definitely an alternating series, but the real question is, does it need to alternate to converge, or is it strong enough to stand on its own? Let's find out.
We just follow the plan. Step 1, check for absolute convergence. So we strip away that alternating part, the -1 to the n. What's left? The sum of 1 over n cubed. And ding, ding, ding. That should be ringing a bell. It's a piece series where p is equal to 3. And since 3 is greater than 1, we know for a fact that this piece series converges.
And just like that, we're done. Since the absolute series converges, we don't even need a step 2. Our original series is absolutely convergent. It's the sturdy kind. Okay, now for a true celebrity in the world of infinite series, the alternating harmonic series. I'm telling you, this is probably the most important example in this whole topic, and for good reason. It's the perfect illustration of what conditional convergence really means. Let's run the test. Step 1, check the absolute series. When we do that, we get the sum of 1 over n. That is the famous harmonic series, and we all know it diverges. So, right away, this thing is not absolutely convergent.
That means we have to go to step 2, check the original series. And using the alternating series test, we can see that yes, the original series does converge.
So see what happened? The original converges, but its absolute version diverges. That is the textbook definition of conditionally convergent. This is our poster child for fragile house of cards convergence.
For our last case, let's try something that looks a little more intimidating. The sum of sine of n over n squared. Now, that sine of n on top, it's not a nice clean +1 -1. It's bouncing all over the place. So how in the world do we deal with this?
We don't panic, we stick to the plan. Step 1, check the absolute series. That's the sum of the absolute value of sine of n over n squared. Now the key here is the comparison test. What's the one thing we know for sure about sine of n? No matter what n is, its absolute value can never be bigger than 1. That means every term in our series has to be smaller than the corresponding term in the series 1 over n squared. And since 1 over n squared is a convergent p-series, our smaller series must converge too.
And there you have it. The absolute series converges, which means our original tricky-looking series is absolutely convergent. Turns out it was another one of our sturdy, rock-solid series in disguise.
Okay, so we've learned how to classify series. But so what? Why do mathematicians make this distinction? What's the payoff? Well, this is where things get really, really interesting. And honestly, a little bit weird.
There are two huge reasons this matters. First, and this will blow your mind, is rearranging terms. With an absolutely convergent series, you can shuffle the terms in any order you want, and you'll always get the same sum. But with a conditionally convergent series, you can reorder the terms to make it add up to literally any number you want. Pi, -10, a billion, you name it. It completely breaks our intuition about addition. Second, and this is super practical, powerful tools like the ratio test and the root test are basically blind to conditional convergence. They're designed to sniff out absolute convergence, so if you use them on a conditionally convergent series, they'll just be inconclusive every time.
And that leaves us with a final thought to chew on. Our entire intuition about arithmetic is built on finite numbers. But as we've just seen, some of those fundamental rules just shatter when we step into the world of the infinite. If the order in which we add an infinite list of numbers can completely change the answer, it forces us to ask, what does it really mean to sum something forever? And what other surprises does infinity have waiting for us?